Last time we talked about arithmetic sequences in series, and right now we're going to talk about geometric sequences in series. So let's take a look at kind of our objective for this lesson. And can as I just said, explore geometric sequences in series. We'll talk about the difference between those and arithmetic as well. So I can't remember if you saw this yesterday with the arithmetic, but again, here's our sequence. How are we going from one to the next? How do I go from 4 to 12, 12 to 36? Go from 4 to 12 by multiplying by 3, 12 to 36 by multiplying by 3, and so on. So because now I am multiplying, this turns into what is called a geometric sequence as opposed to the arithmetic. Arithmetic is where you are adding to get to the next term. There's the definition. Again, you by multiplying the previous term by a common ratio. So you have your geometric sequence as we do right here. And just like we had a way of finding the common difference with an arithmetic sequence, we have a way of finding the common ratio with our geometric sequence. So I'll primarily use this one. You take a certain term and divide it by the a sub n minus 1, which is the previous term. Doesn't matter which two terms you use. The certain term divided by the previous one will give you your ratio. So some you can figure out, like this one for certain. But again, just an example. Here's my ratio. I'm going to take 36 divided by the previous term 12. 36 divided by 12 is clearly 3. So our ratio is 3. Same type of thing there for number 2. Our ratio is going to be 1/4 divided by 1/2. That's going to equal 1/2. So I go from one to the next. 1 times 1/2 is 1/2. 1/2 times 1/2 is 1/4, and so on. So that's how we find our common ratio. And even if there's some that you don't know exactly what they are, I would recommend doing this real quick and making sure you're aware of which is the ratio, or what is the ratio. You'll come across questions like this, 18th term of that sequence. So just like it was with the arithmetic, it can get very tedious to find if I was to list out all 18 terms. So we're going to have a formula for that. With this, here's our formula right here. A sub n equals a sub 1 times r raised to the n minus 1. Very similar to the arithmetic. A sub 1 is the first term. R is the common ratio. N is still the number of terms. And then a sub n is still the nth term. So some similarities between the arithmetic. Again, a sub 1 is still the first term. A sub n is still the nth term. N is still the number of terms. That has not changed. What has changed is now we have R, common ratio, as opposed to D, which is the common difference. So back to this example then. Again, like it said, like it asks, 18th term of that sequence. So let's list a few things that we know or first I'll even write out the formula for us. A sub n equals a sub 1 times r to the n minus 1. So let's list what we know. We have a sub 1 is 1/64. We have n equals 18. That is the number of terms. And then we have our ratio, which is what we need. How do I go from 1/64 to negative 1/32? And again, when they alternate signs like this, you can know that the ratio is going to be negative there. So I'm going to take negative 1/32 divided by 1/64, and that's going to give me negative 2. So my ratio here is negative 2, and again, we knew it was going to be negative because we're alternating signs between these terms. So now with it's kind of just a plug into our formula here. So a sub n equals a sub 1, 1/64 times negative 2 to the 18 minus 1. A sub n equals 1/64 times negative 2 to the 17th. I'm going to switch some things around here. 64, another way to write that is going to be 1/2 to the 6th. And negative 2 to the 17th is negative 2 to the 17th. That's negative. I'm sorry, it's a negative to an odd power, so it's going to give us a negative number. So a sub n equals negative 2 to the 17th over 2 to the 6th. A sub n equals negative 2 to the 11th. And you guys all know what 2 to the 11th is. A sub n equals negative 2048. So a sub n, another way to think about that is a sub 18, that's the 18th term, is negative 2048. Either way, either notation is completely fine for that answer. Find the sum of the first 18 terms, just like it was with the arithmetic stuff. Now we're getting into the kind of adding here and adding terms to figure out what the sum is. So that is now a series. It was a sequence just a minute ago, and now it is a series, same type of thing from the arithmetic, so that has not changed, which is nice in that regard. So what we know here, what we'll need here is another formula. We derived one yesterday for the arithmetic. We're not going to do that here. I'll just go ahead and give it to you. There you have two options based on what you have. If you have a sub 1, r, and n, I would recommend using this one. If you have a sub n, you can go ahead and use the second one. Two different options, again, just depending on what you have in the particular problem. So back to this then, find the sum of the first 18 terms. So it's the same sequences or same series as we had before. So S sub n, I'll give you the formula here, equals a sub 1. We have a sub 1, we have the ratio, we have n, so we're going to use that first one from the previous slide, minus a sub 1 times r to the n, all over 1 minus r. Plugging in what we know, we have S sub 18 terms, sum of them 1 over 64 minus 1 over 64 times negative 2 to the 18th, all over 1 minus r, which is negative 2. So you're going to be plugging this a lot into your calculator, which is going to be helpful for you. 1 over 64 minus 4096 all over 3. And I'd like a fraction for this, but you guys knew that. S sub 18 equals negative 87, 381 over 64. Moving on, kind of an application problem. It says you buy a car for $25,000. The car depreciates by 10% each year. Assuming the rate continues annually and repeats, what will your car be worth in 7 years? What about 12 years? So this is not asking for the sum of them. It's asking for how much it will be worth in that year. So this is asking for a specific term. So this is our geometric sequence. So let's list what a sub 1 is. We have two separate problems here. A sub 1 is going to be that initial price, which is $25,000. And then our ratio now, this is what we have to think about, a little extra thinking here. If it's depreciating by 10%, that means it's holding 90% of its value. So what that means is we want to multiply each value by 90.90 by 90% to get the next value. So our ratio is 0.90. So we're going to set up two of these, after 7 years and after 12 years. So a sub 7 is going to look like this. $25,000, that's a sub 1, times the ratio, 0.9 raised to the 7 minus 1, n minus 1. We're also going to have a sub 12, 25,000 times 0.9 to the 12 minus 1. So again, just calculator work here. So after 7 years, or within 7 years, your car is going to be worth $13,286.03. And then after 12 years, again, kind of just plugging it all into your calculator, a sub 12 is going to be, your car is going to be worth $7,845.26. So again, this is being able to tell the difference between a sequence and a series. If it asks you for the sum, that is talking about a series. If it does not, that is talking about a sequence. So we're going to look at this next one now. This following is a series. So a sub 1 equals 10. The ratio is 1/2. It says, look what happens to the sum as n increases. N is the number of terms. So we're talking about a sum, we're talking about a series here. N is the number of terms. So what's going to happen to this series as I add more and more terms to it? And so we can just think about that right now. What happens when you add more and more of something? If you're adding numbers, that number is going to increase and increase and increase. And so that's what we want to look at. And so I'm going to plug in some different values here. So let's first start with, I'll give you some hypotheticals. I'll pause the recording for a second to look, so I can write it down real quick. But we're going to look at S sub, we'll start with S sub 10. Well, I'll even go back. Let's do S sub 5. Let's add 5 terms together. And then let's add 10 terms together. Let's do 20. And then 30. So give me 1 second while I fill this out. So there's those values plugged in. There's S sub 5, 19.375. Again, I'm adding more terms. S sub 10, 19.9804. Adding more terms. S sub 20, 20 terms this time, 19.999. So as we talked about on that previous slide, just a bit ago, I guess, as we add more and more terms, add more and more things to this sum, our number is increasing. Now the amount is increasing, is getting smaller, and we're going to do one last one. I'm going to do 32 terms. So when I plug in 32 terms, same process, 10 minus 10 to the 1/2 to the 32nd, all over 1 minus 1/2. When I plug that in, it gets me to 20. Now let's jump up and do one more. I mean, let's change colors now. Let's go S sub 50. When I plug this in, so again, a lot of the same stuff, 10 times 1/2 to the 50th, all over 1 minus 1/2. This also is going to give me 20, which seems strange because we said, again, if we're adding more and more of something, it should continually increase. But what happens is it's not going to increase, and we're going to reach a limit. And the limit that it converges to, that's the term, is going to be 20 in this case for this particular series that has this first term of 10 and a ratio of 1/2. So what this turns into, again, if we're adding more and more terms forever and ever, that sounds like it's going to be infinite to me. So this is called an infinite geometric series. So this is kind of where we're going to get our formula from. But there is our formula for the sum of an infinite geometric series. Now this is completely different. There's not a particular set of terms. Clearly it's infinite. It goes on forever. But the key here, normally we don't talk about this too much, but the key here is this right here. The ratio, the absolute value of the ratio has to be less than 1. If it's not, then the series does not converge and you cannot have a sum. It does not exist. So you have to have a ratio that is less than 1, whether it be a fraction or a decimal. It has to be less than 1, otherwise the sum of the infinite series does not work. So let's do a couple more examples here. Find the sum of this series right here. Here's our formula. S sub infinity equals a sub 1 over 1 minus r. So a sub 1 in this case is 1. Our ratio, how do I go from 1 to 1/2, 1/2 to 1/4? Sounds like I just multiply by 1/2. And so now plugging things in, the sum of this series, again, I'm adding more and more things every time. The sum of this series is going to be 1 over 1 minus 1/2, which is 1 over 1/2, which is 2. So the more and more I add here, I'm going to eventually get to 2. Even though it doesn't seem like I'm adding more and more and more, it doesn't seem like I'm never going to get there, or it's going to seem like I'm going to add more than 2. But it's always going to converge to 2. Another example of using the infinite geometric series formula is it says this example right here, represent 0.81 repeating as the quotient of 2 integers. And the quotient of 2 integers, I think we've talked about this a time or two in the year so far, is just a fancy way of writing a fraction. So to change this to a fraction, and I think you guys have probably learned it or at least seen it somewhere in another math class, maybe in middle school or somewhere. But this is going to be a little different. I want to use the geometric sequence or series formula in that process to solve this. So 0.81 repeating. Another way to write that is 81, 81, not 88, 81, 81, etc. Clearly that's going on forever. So if I'm splitting this up again, thinking geometrically, my first term, a sub 1, is going to be 0.81. My second term would be 0.0081. My third term, and you guys can pick up on this, 0.000081, and so on. So this helps us find our ratio, and we can tell what our ratio is from here. I have two numbers that are repeating, so our ratio for this is going to be 0.01. So that's our ratio. Multiply all of these by 0.01. That'll give me, adding these zeros again, this will go on forever clearly. It's repeating. So our ratio is 0.01. Our a sub 1 is 0.81. We have our formula. S sub infinity, again, this is the method that I want to see used, equals 0.81 divided by 1 minus 0.01. So S sub infinity equals 0.81 over 0.99. We can get rid of the decimals if we want. 81 over 99, which is going to reduce to 9/11. So again, using the infinite geometric series formula, this is the work that would correspond with that. So 9/11 is how you write 0.81 repeating as a fraction. So one last one. You guys might have heard about the stimulus checks that are coming, that are being sent to people across the country. I don't think they're being sent to high schoolers. Sorry about that. But these numbers are a little off, but it gets the point across. It says the stimulus check of $1,000 is given. It is known that the spending rate is 90%. What is the overall amount of spending generated by the single $1,000 stimulus check? So that's the goal of the stimulus checks that are being sent out. The economy is, again, kind of in a standstill right now with the virus going on. So we want to promote the economy by giving people money that they then go in turn and spend somewhere. Doesn't matter where it is, but they're looking for that, looking to boost the economy by getting money spent out somewhere. So what we have to think here, the key is, this is underlined as well, how much spending is generated. So $1,000 is given out, but $1,000 is not being spent. What's being spent, and therefore our first term, a sub 1, is going to be 90% of $1,000. And that clearly is $900. So that would be my first term. What my second term would be is going to be 0.90 times the 900. And that's going to give you $810. So let's say you get $1,000, you don't spend all of it, you only spend $900. You go to another store, and then, or you pay your money to a certain store. That store takes that money and then goes to another store and spends only $810. So everybody is only spending 90%. They're always keeping 90%. If I wanted my third term here, again, it would be 90% of that $810, which would be $729. A sub 4, this would be $656.10, and so on. So everybody's only spending 90% of that amount that they are receiving. So this, again, going on forever, this turns into an infinite geometric series. We have our first term. Now we just need our ratio. When you talk about what our ratio would be, our ratio is going to be that 90%. Again, the key to a problem like this, that first term is not the $1,000, it is the $900. So plug this into our formula. We have S sub infinity equals 900 divided by 1 minus 0.9, and that's going to equal $9,000. So we give one person $1,000. The government gives one person $1,000. That's going to generate $9,000 worth of spending. Again, the goal is to boost the economy in some way. So that is section 8.3 continued. Let me know, email me, or reach out to me in some certain way if you have questions on any of that.